The Model-Based Embedded and Robotic Systems Group at MIT is collaborating with the Jet Propulsion Laboratory at Caltech on a project that will enable astronauts to safely work with robots in an easy and intuitive way. One example of such a robot is Athlete, a vehicle developed at JPL that will support robotic and human missions on the surface of the Moon. Athlete is capable of rolling or walking over extremely rough or steep terrain and can load, transport, manipulate, and deposit payloads to any desired sites of interest. Previously, robots have been simple enough to be controlled through teleoperation or direct commanding. However, more complex robots like Athlete or the Vecna Bear battlefield robot have too many degrees of freedom for direct teleoperation or commanding to be practical. We've developed a different control paradigm that incorporates verbal commands, shared written instructions, and demonstration by example to enable more efficient interaction. These modes of communication occur naturally to humans during collaborative tasks. Here is an example of a common-sense written plan where the human and athlete work together to collect rock samples for analysis. The instructions include descriptions of both the human's tasks and athlete's tasks. A key challenge to executing tasks is grounding terms like pick up into athlete motions. We reduce time and effort required to do this by teaching actions through demonstration. We use an interface device called TRACK, developed by the Distributed Robotics Lab at MIT, to teleoperate the robot through each desired activity several times. Here we're teaching athlete the term pick up by showing athlete how to pick up an object without hitting the box. Based on the demonstrated motions, our learning algorithm generalizes from the examples a set of motions that will likely achieve the action of pick up. This is compactly encoded in a representation we call a probabilistic flow tube. Once athlete learns the activity, it can autonomously execute the corresponding nominal trajectory. The learned flow tube represents flexibility in the motions the robot can choose to perform, enabling it, for example, to recover from disturbances. The width of the flow tube indicates areas with more or less flexibility. After athlete knows how to perform each of its tasks individually, it can collaborate with a human to execute the written plan together. We have developed an executive that allows athlete to make decisions at runtime to improve the likelihood of successfully completing the plan. Specifically, athlete schedules the start times and durations of each activity with flexibility, while ensuring that limbs synchronize successfully. This allows it to react appropriately to the human and still perform the actions correctly. We demonstrated our capabilities by integrating them with the athlete prototype at JPL, and by showing a human and athlete cooperating to complete this task. First, the human attaches a gripper to athlete's left limb. The executive timestamps this activity duration when the person is done so it can accommodate changes in the human's activities. Now, athlete is moving the gripper near the rock in preparation to pick it up. This complex motion was learned using the techniques described earlier. Since athlete can't sense the precise location of the rock, the person can assist athlete by fine-tuning the gripper location through voice commanding.
Move limb 6 forward 5 centimeters.
Next, the human attaches a bin to athlete's right limb. The gripper closes on the rock to pick it up. At this point, both limbs move in position to drop the rock into the box. Finally, athlete stores the box for transport, which is the end goal of the plan. In the future, we plan to demonstrate these capabilities with more complex plans that involve a human safely coordinating with multiple robots. Engineers at JPL are currently developing the next generation of athlete robots called Triathlete, in which each robot has 3 limbs and can coordinate together to transport habitats and perform more complex manipulation tasks. In the future, we aim to show humans working safely in the same environment as the triathletes in order to support future operation on the Moon. Funding for this task was provided through the JPL Strategic University Research Partnership Program and the National Defense Science and Engineering Graduate Fellowship.